Continue from thermal analysis. We have already discussed various techniques come under the heading of the thermal analysis. Thermal analysis techniques and method: thermal gravimetric analysis, differential thermal analysis, differential scanning calorimetry, dynamic mechanical analysis, thermomechanical analysis, and thermometric titration. Already we discussed two techniques: thermogravimetric analysis TGA, differential thermal analysis DTA. Now in this lecture we will discuss the differential scanning calorimetry DSC. Let's see the background of DSC. Differential scanning calorimetry is one of the thermoanalytical techniques. All the thermal analysis are the thermoanalytical techniques. A calorimeter measures the heat into or out of the system, out of a sample. A differential calorimeter measures the heat of sample relative to a reference. Sample relative to reference is a differential. Differential means a difference. The calorimeter that measures the difference between sample and the reference. This is our differential calorimeter. The differential scanning calorimetry does all the above and heats sample with a linear temperature ramp. DSC is a technique in which the difference in the amount of heat required to increase the temperature of the sample and reference are measured as a function of temperature. But the sample and the reference are maintained at nearly the same temperature throughout the experiment. So in this technique, everything is moving around the heat. It means the heat content of a system. When we're talking about the heat content of the system, so this heat content of the system is the enthalpy. So what is the enthalpy? The enthalpy is the thermodynamic quantity equivalent to heat content of the system. So the principle of DSC is used to measure the enthalpy changes due to the changes in the physical and chemical properties of a material as a function of temperature or time. So it is all related to the heat content, and heat content indirectly related to the enthalpy, and enthalpy is related to thermodynamic properties, thermodynamic functions. So enthalpy is a thermodynamic function. Let's discuss about the instrumentation of DSC. There are mainly two different type of DSC instruments: heat flux DSC, power compensated DSC. Let's firstly the instrumentation of heat flux DSC. This is a block diagram for DSC operators. DSC heat flux apparatus, sample and reference holders. These are the parts of this heat flux DSC instrument. Aluminium or heat pan placed on Constantan disc. Copper nickel alloy, also known as Eureka. What is Constantan disc? Is made of copper and nickel alloy. This is also called the Eureka. It usually consists of 55% of copper and 45% of nickel. Sample and reference holders are connected to a low resistance. Here is a block diagram. At the right side of this block diagram, we have a lid that is covered the whole system, the whole furnace, you can say, in other words. And the sample pan, chromal disc, chromal wire, and the left is aluminum wire. The right side bottom heating block. One is thermocouple junction, thermoelectric disc, Constantan, reference pan, and purge gas inlet. You all the familiar with the purge gas. We can use different type of gases in DSC also: nitrogen, argon, carbon dioxide, and etc. And thermocouple is a sensor that measures the difference of temperature between two objects. Object means the reference and the sample. The sensors in the DSC instrument: the chromal, an alloy made of 90% nickel and 10% chromium. Constantan area thermocouples. Differential heat flow. Heat flow means difference of heat between two objects. Mean one objective sample, other is reference. Chromal aluminum. an alloy consisting of approximately 95% nickel, 2% manganese, 2% aluminium, and 1% silicon. This type of this is also a thermocouple that measure the difference of temperature between two objects, that is measure the sample temperature. Thermocouple is a junction between two different metals that produce a voltage due to the temperature difference. Now the furnace, one block for both sample and reference cells is called the furnace. The holder means two object holder in Dsc instrument is the furnace. Temperature controller, the temperature difference between the sample and the reference is converted to differential thermal power, which is applied to the heaters to maintain the temperature of the sample and the reference at the programmed value. Heat flux Dsc. In heat flux Dsc, the difference in heat flow into the sample and the reference is measured while the sample temperature is changed at constant rate, that is fixed in temperature program. The main assembly of Dsc cell is enclosed in a cylindrical silver heating block which dissipates heat to the specimen via a constant disc which is attached to the silver block. The disc has two raised platforms on which the sample and reference pans are placed. This is evident from this block diagram. The raised one is sample pan, other is reference pan. A chromal disc and connecting wire are attached to the underside of each platform, and resulting chromal constant thermocouples are used to determine the differential temperature of interest. Aluminum wires attached to the chrome disc provide the chromal aluminum junction for independently measuring the sample and the reference temperature. A separate thermocouple embedded in the silver block serves as a temperature controller for the programmed heating cycle, and inert gas is passed through the cell at a constant flow rate of about 40 ml per minute. This is a purging gas. The purging gas depends upon the nature of the sample, which type of gas we have to purge. For example, any nitrogen, it may be nitrogen, maybe carbon dioxide, maybe argon, and so on. The other type of Dsc is power compensation Dsc. The same, this is a very simple equipment comparative to high flux Dsc. Sample holder, aluminium or platinum pans. Two pans can be seen from the block diagram. One pan is for the sample, other pan for the reference. Similarly, this also have the sensor. The sensor used for the measurement of the temperature. Platinum resistant thermocouples, separate sensors are heated for the sample and the reference. Block diagram you can see the sample and reference pan are placed on a heat sink. And what is the heat sink? Heat sink is a passive heat exchanger that transfers heat generated by electronic device or fluid medium. So this is an electronic device. So this is this heat sink serves as a heat exchanger. Again, the furnace, separate block for the sample and reference cells. Temperature controller supply the differential thermal power to the heater to maintain the temperature of the sample and reference at the programmed value. In power compensation Dsc, the temperature of the sample and reference are kept equal to each other, while the both temperatures are increased or decreased linearly, mean in a linearity way. The power needed to maintain the sample temperature equal to the reference temperature is measured. In power compensation Dsc, two independent heating units are employed. These heating units are quite small, allowing for rapid rates of heating, cooling, and equilibrium. The heating units are embedded in a large temperature control heat sink. As I already told you, what is the heat sink? Heat sink is basically a heat exchanger. Differential scanning calorimetry, the sample and reference holder have platinum resistant thermometers to continuously monitor the temperature of the material. Both sample and reference are maintained at the programmed temperature by applying power to the sample and the reference heaters. The instruments record the power difference needed to maintain the sample and the reference at the same temperature as a function of programmed temperatures. Power compensated Dsc has lower sensitivity than heat flux Dsc, but its response time is more rapid. But in modern analysis, usually heat flux Dsc are used because more sensitivity is required for the analysis in quality control labs. Now the sample preparation in differential scanning calorimetry accurately weighed the sample about 3 to 20 milligram. The sample material and configuration should be used for sample and the reference. Material should completely cover the bottom of the pan to ensure good thermal contact. Good thermal contact means it completely acquired the temperature that is programmed. As a result of Dsc analysis, we get a data in the form of graph. That graph is called the Dsc curve. The result of a Dsc experiment is a curve of heat flux versus temperature or time. There are two different convention exothermic reactions in the sample shown with a positive or negative peak depending upon the kind of technology used in the experiment. This curve can be used to calculate the enthalpy of the transitions, which is done by integrating the peak corresponding to a given transition. Enthalpy of transition can be expressed using equation delta H is equal to Ka, where delta is the enthalpy of the transition, K is a calorimetric constant, and A is the area under the peak. The calorimetric constant varies from instrument to instrument and can be determined by analyzing a well-characterized material for known enthalpy of transition. The area under the peak is directly proportional to the heat absorbed or evolved by the reaction. Height of a peak is directly proportional to the rate of the reaction. From the graph you can say. In the last lecture in DTA, we discussed about the maxima and minima of the curve, but also in Dsc curve, we have to in this presented graph we have a maxima and minima. The minima represented the endothermic peak, while the maxima represent exothermic peak. In endothermic peak, usually heat is absorbed, while in case of exothermic peak, heat is released. Various factors affect the Dsc curve. Two types of factors affect the Dsc curve. Instrumental factors. In instrumental factor, furnace heating rate, recording or chart speed, furnace atmosphere, geometry of the sample holder, location of sensors, sensitivity of the recording system, composition of sample containers. We already discussed what kind of container of sample holder we have to use, which are unreactive on not reacting with the sample under investigation. Second one, the sample characteristics also affect the Dsc curve. The amount of sample, nature of sample, sample packing, solubility of evolved gases in the sample, particle size, heat of reaction, and thermal conductivity also affect the Dsc curve. Now, by various examples, we will discuss the application of Dsc. For example, the determination of heat capacity of a polymer. A Dsc plot can be used to determine the heat capacity. What is the heat capacity? Heat capacity is the amount of heat to be supplied to a given mass of material to produce a unit change in temperature. Unit change means delta change, delta T. Dsc plot can be used to determine a heat capacity when a polymer is being heated. When we start heating two pans, the computer will plot the difference in heat output of two heaters against temperature, that is plot of heat. absorbed by the polymer against temperature. From the graph you can see one side is heat flow, other is temperature. Temperature is along x-axis and heat flow is y-axis. So then from this graph heat capacity of the polymer can be determined. Heat flow is the heat supplied per unit time t, whereas the heating rate at temperature increase delta t per unit time. Heat flow is equal to heat over time mean Q over T. Q is the heat, T is time. Heating rate, temperature increase over time. Temperature increase delta T over T. Delta T is capital T for the temperature, small t for the time. By dividing the heat flow Qt by the heating rate delta T over T, it ends up with heat supply divided by the temperature increase, which is called heat capacity. So heat capacity is equal to Cp, Q over delta T. By using Dsc, we can determine the glass transition temperature of the polymers. This means there is a more heat flow. There is increase in the heat capacity of the polymer. This happens because the polymer just gone through the glass transition. Now everybody is familiar with the glass transition. Gradual or reverse transition in amorphous material from hard or relative glassy state to viscous rubber state is the transition, is a glass transition, and the temperature that is measured at this stage is called the glass transition temperature. It is a reversible transition in amorphous material from a hard brittle state into molten rubber-like state. Because of this change in heat capacity that occurs at a glass transition, we can use Dsc to measure a polymer's glass transition temperature. From the graph, again you can see the temperature and heat flow, XO and NO, as already discussed in this Dsc and in the former lecture, XO and NO type of reactions. So from the graph you can see the glass transition temperature, the midpoint when it sleep down and show a minima, minima, the midpoint of that minima is a glass transition temperature. From Dsc we can measure the phenomena of crystallization after glass transition. This particular polymer have a lot of mobility. They wiggle and squirm and never stay in one position for a very long time. Wiggle and squirm is move up and down with small movement side by side as wiggle and squirm. But when they reach the right temperature, they will give off enough energy to move into ordered arrangement, which are called the crystal arrangement. In amorphous state, there is no ordered arrangement, while in case of crystal, there is an ordered arrangement of all the atoms. When polymer fall into these crystalline arrangements, they give off heat, so it does not have to put out much heat to keep the temperature of the sample pan rising. This drop in heat flow as a big peak in the plot of heat flow versus temperature. The temperature at the highest point in the peak is usually considered to be the polymer's crystallization temperature, that is Tc. Again from the block diagram, from the curve you can see XO and NO heat flow is along y-axis, temperature is on x-axis. From the graph, the maxima representative Tc. Tc is a polymer crystallization temperature. Also, the area of the peak can be measured, which tells us the latent energy of crystallization of the polymer. But most importantly, this peak tells us that the polymer can in fact crystallize. The latent heat is heat absorbed or evolved during a constant temperature process is latent heat energy, is called the latent energy. Melting the polymer, if polymer is heated past a Tc, eventually reach another thermal transition called the melting. When polymer's melting temperature is reached Tm, Tm is a melting temperature, the polymer crystal begin to fall apart, that is they melt, it comes out of their ordered arrangement and begin to move around freely. That can be spotted on a DC plot. after Tc. Tc is the crystallization temperature, Tm is melting temperature. The heat which polymer give off when crystal is absorbed when reached at Tm. So Tm also endothermic process. This is a minima. Now all the properties melting, crystallization put together, both melting and crystallization involve giving off or absorbing heat. The glass transition temperature is a change in heat capacity of the polymer, because there is a change in heat capacity and there is no latent heat involved with the glass transition. The glass transition is second order transition. Transition like melting and crystallization, which do have latent heat, are called first order transition. The first order transitions are the such transition the system either absorb or release a fixed amount of energy per volume, that absorb or release fixed amount of energy. So in this curve, again temperature is along x-axis, heat flow is along y-axis, Tg, Tc and Tm. Tm is the melting point, Tc is the crystallization temperature. So Tg and Tm are endothermic, while Tc is the exothermic process. It can easily be seen from maxima and minima. Maxima is Tc, while the minima is Tm and Tg. The Tg at glass transition. Liquid crystals. Dsc is used in the study of liquid crystals. Some material go from solid to liquid. They go through a third state which displays properties both the phases. This anisotropic liquid is known as liquid crystalline state or mesomorphic state. So we already discussed about the liquid crystals, the state of matter which have property between those of conventional liquid and of solid crystals is called the liquid crystal. This is also called the mesomorphic state. Using Dsc, observe the small energy changes that occur as matter transition from a solid to liquid crystal and from a liquid crystal to anisotropic liquid. Using the Dsc, we can also study the oxidative stability. To study the stability to the oxidation of sample generally requires an airtight sample chamber. Various materials or drugs, foods, instructions with must be placed in airtight containers. Why the instruction is given? Because they react with oxygen from the environment and spoil, and chemical changes are occurred as well as the microbiological changes occurred. To check the oxidative stability of these type of material, Dsc can be used. Usually done isothermally at constant temperature by changing the temperature of the sample. First, the sample is brought to the desired test temperature under an inert atmosphere, usually nitrogen, then oxygen is added to the system. Firstly, the nitrogen purges, sample is purged with the nitrogen, then oxygen is passed to the system. Any oxidation that occurs is observed as a deviation in the baseline. We get a baseline in the Dsc curves. If any deviation occurs, we can assess in the inert atmosphere the sample goes under oxidation. So Dsc is an important technique for the oxidative stability of the samples under investigation. Such analysis can be used to determine the stability and optimum storage condition for a material or compound. That is, with the clear instruction, this type of material must be stored in airtight container. The material may be drugs, maybe food items, or any other type of materials. For using Dsc, drug analysis can be done. In the pharmaceutical industry, it is necessary to have well characterized drug compound in order to define processing parameters. For instance, if it is a necessity to deliver a drug in the amorphous form, it is desired to process the drug at a temperature below which crystallization can occur. There are various various steps in the tablet formation, capsule formation, injectables, liquid injectables, small volumes and large volumes. These are packed under such environment the amorphous state of the particular drug should be maintained. If the temperature increased, then their amorphousness of that particular drug will be disturbed and that come into the crystalline form. The drugs lose its efficacy if it converted into a crystalline form. Amorphous drug has different efficacy. Crystalline drugs have of a different efficacy. Even the drug molecule is the same. So it depends amorphous and crystalline state of the drug, how is its efficacy to have shown efficacy to a patient. So those drugs which are to placed in amorphous form are processed under the temperature where their crystallization should not occur. General chemical analysis can also be done by Dsc. Melting point depression can be used as a purity analysis tool. This is possible because the temperature range over which a mixture of compound melt is dependent upon their relative amounts. With the impurity, melting amount of any chemical drug molecule compound will decrease. With the impurity, melting point is decreased. Consequently, less pure compound will exhibit a broadened melting dip that begins at low temperature than a pure compound. With running with the reference of pure sample, pure compound and sample. If there is any dip that begins at low temperature, we can determine the purity on the basis of the melting point. This is very important technique. Dsc is important technique for determination of melting point to elaborate the melting point of any molecule compound under investigation. Yeah, food science. In food science, Dsc also used in for the analysis of different food items. In food science research, Dsc is used in conjunction with other thermal analytical techniques to determine water dynamics. Changes in water distribution may be correlated with the change in the texture. Water is important, so important in food items where if water quantity is more than the required amount in the packed food, then this creates the problem in the food items to disturb. If quantity of water is more, then the food will be spoiled. To determine the distribution of water in the food, Dsc is a much convenient technique for determining the food water dynamics in the food atoms. So this is also an important instrument for determination of water dynamics in food sciences. So thank you very much. If you have any question, please put your question in the chat box. I will answer all these questions. Again, thank you very much.